Okay students, let's get started with today's lecture. Today we have to cover A2 physics topical past papers for the chapter of nuclear physics. This is your chapter number 12. Chapter number 12. Okay. So let's see question 1 part A, and this PDF is attached in the Google Drive ka link in the description. State what is meant by binding energy of a nucleus. So the energy required to separate the nucleons in a nucleus to infinity. Simple as that. This is your binding energy. Let's see part B. Figure 9.1 or table 9.1 shows the masses of two subatomic particles and a polonium 212. So you have a polonium 212 nucleus and these are the masses of a subatomic particle. Okay. For the polonium 212 nucleus, determine the mass defect. We have to calculate the mass defect. Okay. So how many protons does polonium have? 84. So polonium has 84 protons. So 84 multiplied by the mass of proton, that is what? 1.007276 minus how many number of neutrons does polonium have? 212 minus 84, this becomes 128. So 128 into your answer of protons, that is 1.008665. Okay, sorry, this will be in plus. This is the mass of the nucleons separately. And what is the mass of the nucleus? Minus 211.9427942749. So let's calculate this. 84 into 1.007276. This is a lengthy calculation, so please do it with a special care. 1.008665 minus 211.942 and 749. So yeah, this is a lengthy calculation. The mass defects come out to be what? 1.777555 U. Now what is this value of U? This value of U is 1.66 into 10 raised to the power of minus 27 kg. And since you have to give your final answer in kgs, you have to convert it 1.77555. And now you can give your answer to 2 decimal places. After this multiplication, you can give your answer to 2 decimal places. 1.66 into 10 raised to the power of minus 27. This comes out to be 2.95, a very simple answer, into 10 raised to the power of minus 27 kg. Yeah, I hope this is correct. Let's verify from the marking scheme as well, because these were very lengthy calculations. Yes, our answer is exactly same as the marking scheme. So let's move on to the next part. You have to calculate the binding energy. How will you calculate the binding energy? E is equals to change in m, that is the mass defect, into c square. What is your mass defect? 2.95 into 10 raised to the power of minus 27 multiplied by what is the speed of light? 3 into 10 raised to the power of 8 whole square. So let's multiply it. 3 into 10 raised to the power of 8, and this becomes your whole square. Okay, this will be equal to what? Energy is equals to 2.65 into 10 raised to the power of minus 10 joules. Simple as that. Now you have to calculate binding energy per nucleon. So that's also pretty easy. How many nucleons do we have? 212. What is the binding energy? 2.65 into 10 raised to the power of minus 10. So 2.65 into 10 raised to the power of minus 10 divided by 212 will give you your binding energy per nucleon. Let's calculate it. This becomes 1.25 into 10 raised to the power of minus 12 joules. Simple as that. Let's further move ahead. On figure 9.1, sketch the variation with nucleon number of binding energy per nucleon for values of A from 1 to 250. Okay. So as your nucleon number is going from 1 to 250, you have to tell about the binding energy per nucleon. So we know that binding energy peaks at iron. Binding energy peaks at iron somewhere here, and then it starts to decrease. Something like this. Let's correct this graph. Something like this. Yeah. Okay, so let's further move ahead. On your line in 9.1, draw an X to show the appropriate position of polonium 212. So polonium 212 has how many number of nucleons? 212. So its position will be somewhere here. Let's mark a X here. Okay. Now let's move on to the third part. Polonium 212 is radioactive and undergoes alpha decay. Okay. So this particle undergoes alpha decay. Okay. Suggest and explain with reference to figure 9.1 why the alpha decay of polonium 212 results in a release of energy. Why will the alpha decay of polonium 212 release energy? Because it gets more stable by releasing energy. Binding energy per nucleon becomes greater. Okay, so what can you write here in this answer? You can say that the total number of nucleons decrease. The total number of nucleons decrease. Why? Because you are undergoing an alpha decay. The total number of nucleons decrease. Hence, the binding energy per nucleon increases, resulting in a stable isotope, simple as that. Let's move on to the next question. Also, you can download this document from the description below. The marking schemes are also attached. You can verify your answer. Define half-life of a radioactive isotope. What is the half-life of a radioactive isotope? The amount of time. Yeah, you can skip the word of amount. The time taken for the activity of a nucleus to half. The time taken for the activity of a nucleus to half is known as half-life. Okay. Radioactive isotope X decays to isotope Y. Okay, so X is decaying to isotope Y. Simple as that. Okay. A sample contains only nuclei of X at time t is equals to 0. So at time t is equals to 0, this is your graph of X. At time t is equals to 0, you have only X. Figure 9.1, okay, shows the variation with time t of the numbers of nuclei X and Y as the sample decays. Okay, so this graph is showing how X is decreasing as time increases and how Y is increasing as time increases. State the name of the quantity represented by the gradient of line X in figure 9.1. Okay, so let's say this is figure 9.1. You have plotted number of nucleuses on the y-axis, time on the x-axis. Number of nucleus divided by time is equals to what? Do you remember? It used to be equal to activity. But a change in time over change in number of nucleuses over change in time is equals to what? Is equals to your activity. So you can write it here. This is equals to your activity. Simple as that. Let's further move ahead. State 3 conclusions about X or Y that may be drawn from figure 9.1. The conclusions may be quantitative or qualitative. Use the spaces below for any working that you need. Okay. First of all, my instinctive behavior here should be that I am starting from 4 into 10 raised to the power of 22 nucleuses. When these nucleuses half, when these nucleuses go from 4 to 2. What is my time? What is the time taken for the number of nucleuses to half? The time taken for the number of nucleuses to half is this value. And this is 13.5. So what can you say? The half-life of isotope X is what? Isotope X is 13.5 seconds. Okay. Now once you have calculated half-life, can you calculate the decay constant? Yes. We know decay constant is equals to what? ln2 over your half-life. What is your ln2 over 13.5? Let's calculate that. ln2, 1 second. ln2 divided by 13.5. This comes out to be 0.051 second minus 1. So your decay constant lambda is equals to what? 0.051 second minus 1. As the third observation, you can see one more thing. That the number of nucleuses at any point, if I basically the sum of nucleuses of X and Y at any point in the graph will remain equal to what? 4. The sum of nucleuses at any point in the graph will remain equal to what? 4 into 10 raised to the power of 22. So let's experiment it at a random point. Let's do an experiment at a random point. Let's say we experiment at this point. Okay. Let's say we experiment at this point at time t is equals to 30. My visual observation is that the number of isotopes at any time period is remaining same. So at time t is equals to 30, the number of isotopes of X is what? 0.9 into 10 raised to the power of 22. And at time t is equals to 30, the number of isotopes of Y is what? 3.1 into 10 raised to the power of 22. Add these two up. You will get the same value, that is 4 into 10 raised to the power of 22. So the number of isotopes remains same throughout. You can write it here. The number of isotopes. You can say the number of isotopes. The number of isotopes remains same. The total number, I think the total number will be a good option. The total number of isotopes remains same throughout. Okay, let's move on to part C. The mass of radioactive isotope X in the sample is this. Okay, so the mass of the sample is this. Okay, at time t is equals to 0. Okay, determine the nucleon number of isotope X. We have to determine the nucleon number of isotope X. So what will we do? We know that this is the mass of isotope X at time t is equals to 0. So this number of mass, this mass is equivalent to how many number of nucleus? This mass is equivalent to 4 into 10 raised to the power of 22 nucleuses. So if I can apply the ratio method here, I can give the headings as well. Let's say this mass is equals to how many nucleuses? This mass is equals to how many nucleuses? 4 into 10 raised to the power of 22 nucleuses. If I have to calculate the mass of one nucleus, what will I do? Cross multiply. This X is the mass of one nucleus. Cross multiply. X is equals to what? 7.3 into 10 raised to the power of minus 4 divided by 4 into 10 raised to the power of 22. Let's calculate it. 7.3 into 10 raised to the power of minus 4 divided by 4 into 10 raised to the power of 22. This comes out to be what? The mass of one nucleus comes out to be 1.825 into 10 raised to the power of minus 26 kgs. So this is your mass of one nucleus. Now I know that the mass of one nucleon is equals to what? 1.66 into 10 raised to the power of minus 27 kg. This is the mass of one nucleon. Mass of one nucleon. Okay. What was the mass of one nucleus? Mass of one nucleus is 1.825 into 10 raised to the power of minus 26 kg. So how many nucleons will be there in my nucleus? Very easy to find out. 1.825 into 10 raised to the power of minus 26 divided by 1.66 into 10 raised to the power of minus 27. Why have I done that? Because I knew my mass of nucleus. I divided it by the mass of one nucleon to calculate the number of nucleons in my nucleus. So my answer comes out to be round about 10.99 and 3. So this is roughly equal to 11 number of nucleons. So nucleon number will be 11. Simple as that. Let's move on to the next question. Yeah, marking scheme also gives the same answer. So yeah, that's perfect. Okay, so let's move on to this question. State what is meant by binding energy of a nucleus. Binding energy is the energy required to move, to separate, you can say, to separate the nucleons in a nucleus to infinity. In a nucleus to infinity. Simple as that. Let's move on to part B. A nucleus of uranium-235 absorbs a neutron and becomes unstable. Okay. It then undergoes a fission reaction. One possible reaction is this. Okay. Determine the number of neutrons produced in this fission reaction. Okay. So we have to determine this number of neutrons in this fission reaction. Very easy to predict. What can we do? Sum up the mass numbers on the left hand side. 235 plus 1 is equals to what? Sum up the mass numbers on the right hand side. 142 plus 90 plus these number of neutrons, that is x. So this becomes what? 236 minus 142 minus 90. The number of neutrons x is equals to 4. So let's move on to the next one. Data for the binding energy per nucleon for this fission reactions are given in table 8.1. Okay. Calculate the energy released in mega electron volts from the fission reaction of one nucleus of uranium-235. Okay. So we have to calculate the energy released during this reaction. How will we do that? Very, very easy. The energy of products minus the energy of the reactants. So what is xenon? Okay, so 142 xenon. How many number of nucleons does xenon has? 142. So multiply this energy 142, multiply this energy by 142, because this 8.37 is the energy per nucleon. And how many nucleons does xenon have? 142. So 142 into 8.37. Plus, what else do we have in the product? Strontium, that has a nucleon number of 90, multiplied by the energy per nucleon, that is 8.27, minus what was your reactant? Uranium-235, into what is the energy per nucleon? 7.95. Let's calculate it. 142 into 8.37 plus 90 into 8.72 minus 235 into 7.59. This comes out to be 189.7 mega electron volts. Let's check the marking scheme as well, whether we have done it correctly or not. 189.7. Yeah, the marking scheme is also giving the same answer. Correct. Let's move on to part 3. The isotope xenon 142 is unstable. The isotope xenon 142 is unstable and xenon 132 is stable. Suggest a reason why xenon 142 is unstable. So the reason is quite obvious and listed in the first line. Xenon 142 is unstable and xenon 132 is stable. Okay. Why is xenon 142 unstable? Yes, why is this thing unstable? Xenon 142 contains a lot of protons, a lot of neutrons in the nucleus. Hence it is unstable. Simple as that. Let's move on to part 4. Xenon 142 decays into an isotope cesium 142. Okay, so xenon 142 decays into an isotope of cesium 142 like this. Okay, okay. A sample initially containing only nuclei of xenon 142. After a time of 6 seconds, the ratio of number of decayed nuclei of xenon divided by number of undecayed nuclei of xenon is equals to 131. Okay. So let's say there is a pie. Let's say it's better to explain it with a pie chart. Let's say this is a pie chart and let's say something like this has happened. Something like this has happened. 1 second. Yeah. So this entire thing is all the thing except the black triangle. The entire circle except the black triangle is the number of decayed nucleuses. This entire yellow highlighted region except the black triangle is the number of decayed nucleuses. So let's write it here. This is the number of decay nucleuses. Okay. And this white triangle, or you can say the blue shaded region, is equals to what? It is equals to the undecayed nucleus. Okay. The examiner is telling us that the number of decayed nucleuses are 31 times the number of undecayed nucleuses. Okay. So can you tell me what is the total number of this initial pie? What will be the total number of nucleuses initially? What will be your N naught? Your N naught will be, let's say, 32. Because initially you have these decayed nucleus as well and undecayed nucleuses as well. Add both of them up. Initially, how many pieces do you have? 32. Okay. And currently, how many are left? How many are left undecayed? 1. Can you see? This undecayed number of nucleuses is your N. Okay. So what can you say here? You know the decay equation. N is equals to N naught E minus decay constant T. N is 1. N naught is 32 is equals to E minus. In place of decay constant, I have told you earlier as well. What can we write? ln2 divided by the half-life, that is represented like this, T and half, multiplied by the time, that is equals to what? 6 seconds. Okay. So now what can you do? You can take ln on both sides. Take ln on both sides. Okay, let's do that. Ln 1 over 32, okay, is equals to minus, let me write it and not do it directly, ln E minus ln2 multiplied by 6 divided by half-life, that is T half. This ln E will get cancelled out. And what will you have next? let me do the entire calculation, otherwise you guys will get confused. Ln 1 over 32 is what? Ln, one second, let me calculate that. 1 divided by 32, yeah, this comes out to be minus 3.466 is equals to minus ln 2, okay, multiplied by 6 divided by half-life. Okay, this minus and minus will get cancelled out, divided by, okay, so half-life comes out to be what? ln2 multiplied by 6 divided by this answer 3.466. so let's calculate it. ln2 multiplied by 6 divided by answer, your half-life comes out to be 1.2 seconds. Simple as that. This is your answer for half-life. Okay, so let's see this question. Fluorine 18-9 is a radioactive nuclei that is used as a tracer in positron emission topography. Okay, tomography. So basically this is a PET scan that we have studied in chapter number 13 in medical physics. Fluorine 18 decays to a nuclide of oxygen according to this formula. Okay, what is meant by a tracer? A radioactive substance introduced in the body. A radioactive substance introduced in the body that can be detected, introduced in the body that can be detected, that can be detected. Simple as that. What is a tracer? A tracer is a radioactive substance introduced in the body that can be detected. Okay, state the symbol of the particle that is represented by X and the values of P, Q and R. So what is represented by X? X is your positron, that is E plus or beta plus. What is the value of Q? That is this thing. This is 0. What is the value of P? That is this thing. It is plus 1. What is the value of R? Very simple. You know that Q is 0. So left hand side you have nucleon numbers of 18. Q is 0 plus R. R is equals to 18 as well. Okay, very simple. Let's move on to B part 1. Explain how radioactive decay of fluorine 18 results in the emission from the body of gamma ray photons that are detected using a PET scan. So how does this leads to the emission of gamma rays photons that are detected using PET scanning? So basically inhalation of photons occur when they combine with electrons. Basically, what is the equation of this process? -1 electron plus positron results in what? Results in the formation of gamma photon. Combined with electron, this results in the formation of gamma photons. And what makes it possible for gamma photons to be detected? Yes, how are gamma photons detectable? So the mass of positron and electrons gets converted into energy that is detectable. Okay, simple as that. Gets converted into energy of gamma photons that is detectable. Simple as that. Let's study the next thing. Explain how the detection of gamma ray photon is used to produce an image of tissue being examined. So image production, the image being formed, depends on two things: the time delay with which gamma photons arrive, gamma ray photons arrive, and what is the second factor that enable the production of image? First factor is the time delay with which gamma photons arrive, and the second factor is the amount of gamma photons arriving from a tissue. Amount of gamma photons arriving from a tissue. This enables us to form the image. Okay, let's move on to part C. The half-life of fluorine is capital T. Okay, a patient is injected with the amount of substance N of fluorine 18. Okay, so if the amount of substance is N, how many atoms or molecules will you have? N is equals to the mole multiplied by the Avogadro's number. If your number of moles is N, how will you calculate the number of molecules? Capital N. Number of moles multiplied by the Avogadro's number. Let me also write it here. This is number of moles, and this is your Avogadro's number, that is equals to 6.2 into 10 raised to the power of 23. Determine an expression for the initial rate of the rate or production of gamma photons. Okay, so we have to calculate the initial rate of production of gamma rays photons by the tracer in terms of Nt and the Avogadro's constant. Okay, so what else do we know? We know that activity of any nucleus or any fluorine atom at any point can be given like this: decay constant multiplied by N. You have already calculated N. What will your decay constant be equal to? Decay constant will be equal to ln2 over capital T, and you have already calculated N as well, that is N into Avogadro's constant. One thing is still remaining here. Do you realize that for every positron and electron there are 2 gamma photons being emitted? So this activity will be multiplied by 2. This will equal to the initial rate of you can say initial rate of production, 2 ln 2 divided by capital T into N capital Na. Something like this should be your answer. Let's also verify it from the marking scheme so that we don't do a blunder here. Yes, see, we have given the correct answer here. 2 ln 2 N Na and T. Okay, they have just formatted it differently. Nothing else. Okay, now let's further move ahead. On figure 9.1, sketch the variation with time t of r. We have to sketch r versus t. So that's very easy. We already know the equation. R is equals to 2 ln 2 N capital Na divided by T. Now if you pay close attention, 2 is a constant, ln 2 is a constant, N number of moles is a constant, Avogadro's number is also a constant. You can replace all of this and say rate of production is inversely proportional to time. So your first point will be here. At time t, your R will become half, and at a time of 2t, let's say somewhere here, your rate of production will become 1 over 4 R naught. So somewhere here, so you can draw a graph like this. Okay, obviously you can make it much better than me with pencil. So let's move on to the next question. Yeah, let's see this. Okay, so define mass defect. What is mass defect? Mass defect is the difference between the mass of the nuclei, and the sum of difference between the mass of the nucleus, you can say, or nuclei, Nucleus will be a better term. Difference between the mass of the nucleus and the sum of individual nucleons separated infinitely. Simple as that. Let's move on to the next question. As I can see, this is again a calculation heavy question. Okay. Table 9.1 shows the mass defects of 3 nuclei. Okay, these are the mass defects of 3 nuclei. The nuclear fusion process in a particular star is described by this. Okay, where X is a particle that has no mass defect. What is X? X is obviously your neutron. Simple as that. Very evident. Show that the energy released when one nucleus of helium is formed in this fusion reaction is this. Okay, we have to show this energy. So first of all, we will calculate the mass defect. How can I calculate the mass defect? Mass of products minus the mass of reactants. Simple as that. So what is the mass of products? What is the mass of products? 0. Again, as I said, you guys, this is a calculation heavy question. 0.3077 minus 0.009105 minus 0.002388. Can you calculate the mass defect here? Yes, 0.30377 minus 0.009105 minus 0.002388. This comes out to be what? This comes out to be 0.0188884 U. Please remember this is in U. So you have your mass defect. Now can you calculate the energy? Yes, that's very easy. Energy is equals to mass defect multiplied by C square. What is your mass defect? 0.018894. What is the value of U? What is the value of U? U is equals to 1.66 into 10 raised to the power of minus 27. What is the value of C? 3 into 10 raised to the power of 8 whole square. So let's calculate this answer. Let me put this in the calculator. I hope we are correct, because whenever we have numbers like these, yeah, the answer comes out to be 2.82 into 10 raised to the power of minus 12 joule. That is same as this. Let's move on to the next one. The star in B has a radius of this. Okay, the star in B has a radius of this and a luminosity of this. Can you see luminosity is in the units of volts? This means this is also considered as power. Okay. All the energy released from the formation of helium is radiated away from the star. Okay, all the energy is radiated away from the star. All the energy that is radiated from the star has been released in the formation of helium-2. Okay, so the star is only releasing energy due to helium formation, and all that energy is being radiated away. Okay, so we have to calculate the mass of helium produced per unit time by the fusion process. Okay, so first of all, you have power, that is 1.4 into 10 raised to the power of 28. This was luminosity, but I have written it as power because both of them are interchangeable. And you have the energy as well. You have the energy as well. Can you see this? You have the energy as well. That is 2.82 into 10 raised to the power of minus 12. 2.82. Oh, 1 second. 2.82 into 10 raised to the power of minus 12 joules. Okay, so now understand a bit. This is the power due to the star. This is the power of the complete star. Okay, this is the energy, and this is the energy due to one molecule. This is the energy due to one molecule, and this is the power of the complete star. Can you calculate the number of helium nucleuses? Can you calculate the number of helium nucleuses? Yes, very easy. What will I do? Power is equals to N, that is the number of helium nucleuses, multiplied by energy of one helium nucleus to get the total energy divided by time. Now your time is equals to 1 seconds. Your time is equals to 1 second. Okay, your time is equals to 1 second, so you can ignore this time. Ignore this. Power is equals to N multiplied by the energy. What is power? 1.4 into 10 raised to the power of 28 divided by energy, that is 2.82 into 10 raised to the power of minus 12. This becomes your number of particles. Let's calculate this. 1.4 into 10 raised to the power of 28 divided by answer. This comes out to be 4.96 into 10 raised to the power of 39 is your number of helium nucleuses, number of helium atoms. But we didn't have to calculate the number of helium atoms. We have to calculate the mass produced. So how will we do that? Very, very easy. The total mass will be equal to what? Total mass produced is equal to what? Mass of one molecule multiplied by the number of molecules. Simple as that. What will be the mass of one helium molecule? Yes. What will be the mass of one helium molecule? The nucleon number is 4 multiplied by the atomic mass unit 1.66 into 10 raised to the power of minus 27 multiplied by the number of molecules 4.96 into 10 raised to the power of 39. Okay, let's do that. 4 into 1.66 into 10 raised to the power of minus 27. This comes out to be, total mass comes out to be 3.29 into 10 raised to the power of 13 kgs. I hope this answer is correct. Let's check it out in the marking scheme as well. Oh, very good. Very, very good. Very proud of myself. This answer comes out to be 3.3 into 10 raised to the power of 13. Simple as that. Okay. Next we have to calculate the surface temperature of the star, that is equals to what? Luminosity is equals to 4 pi Boltzmann constant r square t power 4. You already know the luminosity, that is 1.4 into 10 raised to the power of 28. 1.4 into 10 raised to the power of 28. 4 pi Boltzmann constant is equals to what? 5.67 into 10 raised to the power of minus 8. What is your radius r equal to? Can you see here? Radius r is 2.3 into 10 raised to the power of 9. 2.3 into 10 raised to the power of 9 whole square into temperature power 4. Let's calculate this answer. 1.4 into 10 raised to the power of 28 divided by 4 pi into 5.67 into 10 raised to the power of minus 8 into 2.3 into 10 raised to the power of 9 square. And if I take a 4 power of this will come out to be 7800 kelvins. 7800 Kelvin is your temperature answer. Let's move on to the next question. Plutonium 238 is unstable and undergoes alpha decay. Okay. Complete the equation to show the decay of plutonium 238. So if you are undergoing alpha decay, your nucleon number will decrease by 4, your proton number will decrease by 2. This is 4, 2 as your alpha particle. The power source in a space probe contains 0.874 kgs of plutonium. Each nucleus of plutonium decays to give this amount of energy. The half-life of plutonium is this. Okay, calculate the initial number of plutonium in the power source. We have to calculate N naught. Okay, how will we do that? Very, very easy. So the total mass is what? 0.874 kgs. What is the mass of one plutonium atom? 238, that is the nucleon number, multiplied by 1.66 into 10 raised to the power of minus 27. So let's calculate this. 0.874 divided by 238 into 1.66 into 10 raised to the power of minus 27. This comes out to be what? 2.2 into 10 raised to the power of 24. Okay. Determine the initial activity of the source. Okay, you have to determine the initial activity of the source. Give a unit for your answer. That's also very easy. We have studied that activity is equals to decay constant into the initial number of particles. How will you calculate your decay constant? ln2 divided by your half-life. What is your half-life here? 87.7 years. Let's convert it into seconds. 87.7 multiplied by the number of days in a year, multiplied by number of hours in a day, and multiplied by the minutes in 1 hour, and multiplied by the seconds in 1 minute. And how many particles do you have? 2.2 into 10 raised to the power of 24. 2.2 into 10 raised to the power of 24. Let's calculate this. ln2 multiplied by 2.2 into 10 raised to the power of 24. Okay, let's divide this answer. 87.7 into 365 into 24 into 3600. This comes out to be 5.5 into 10 raised to the power of 14. And what are the units of activity? BQ, or you can say seconds minus 1. Okay, use your answer in part B2 to determine the initial power output from the source due to the decay. So that's very easy. These are the number of particles decaying initially. What is the power due to one particle? 5.59 mega electron volt. So multiply both of them together. 5.5 into 10 raised to the power of 14 multiplied by the power due to one molecule. One nucleus. 5.59 into 10 raised to the power of 6 into 1.6 into 10 raised to the power of minus 19. This is the, let me also tell you, this is the power due to one nucleus, and these are the number of nucleuses. Simple as that. So let's multiply both of them together. 5.59 into 10 raised to the power of 6 into 1.6 into 10 raised to the power of minus 19. This comes out to be 493. The initial power output is 493 volts. Simple as that. Let's move on to the next one. The space probe will continue to function until the power output from the plutonium drops to 65.3% of its initial value. Calculate the time in years for the space probe will function. So that's very easy. We know the decay equation. N is equals to N naught E minus decay constant into time. For how many percentage will this function? 65.3. What is the initial percent? 100%. E minus the decay constant. What is decay constant? ln2 divided by your half-life, that is 87.7 multiplied by t. Now you will notice that I haven't converted my answer from years to second. Why? Because I have to give my final answer of time in years as well. So I haven't converted the time into years because my final answer of time should be in years as well. So I have just kept it like this. Now bring this 100 towards the denominator. 65.3 divided by 100 is equals to E minus ln2 over 87.7 into t. Now let's take ln on both sides. Take ln on both sides. Let's do that. ln 65.3 divided by 100. ln E will get cancelled out. This will give you minus ln2 over 87.7 into t. So your time will come out to be what? Time will come out to be ln 65.5 divided by 100. This gives you a value of minus 0.42. This entire fraction gives you a value of minus 4.2. Okay, this is multiplied with what? 87.7 divided by negative ln2. So let's do that as well. Okay, divide this answer by ln2. Oh, 1 second. Why is the calculator giving maths error? Maybe something wrong here. ln2, yeah, this comes out to be 53. So 53 is the amount of time for which this source can keep providing power. Let's also check the marking scheme because I was getting a maths error initially. Yeah, so 53.5 years or 53 years, correct. Okay, yeah, and our other answers are also correct. That's good. Let's see this. An alternative power source uses energy generated from the radioactive decay of polonium 210. This isotope has a half-life of how many years? 0.378 years. Okay, so polonium 210 have a half-life of 0.378 years. Okay, the mass of the isotope needed for the initial power output is this. Okay, so the mass is considerably low. Can you see? The mass is considerably low. Initially, the mass of polonium 238 was what? 0.874 kg, which is high. So state one advantage and disadvantage of polonium 210. One advantage that I can see right off the bat is less heavy. So less amount of fuel needs to be carried. Less amount of fuel needs to be carried. What is a disadvantage? What is a disadvantage? A shorter half-life. What will be the problem with a shorter half-life? Hence, it wouldn't be able to supply energy for a longer amount of time. So this was the last question of nuclear physics. I hope you like the past previous videos, and if you want to download this PDF, you can download it from the description below. Thank you for watching.